Hi there, and welcome to my video explaining space curvilinear motion from Module A, Kinematics and Gear Analysis. Today I'll be talking about rectangular coordinates, cylindrical coordinates, and spherical coordinates. I won't be referring much to rectangular coordinates, for I assume that you guys are very familiar with them. They're used widely in many areas, and I'll assume you've used them before. Cylindrical coordinates are a little bit different with the system r, theta, and z. I'll be showing you an example with that, and also an example with spherical coordinates, which is capital R, theta, and phi. So I'll be referring to these documents. I won't be deriving them. You can derive them yourself if you wish. You just need to note two simple products. The time derivative in the ER direction is theta dot E theta, and the time derivative in the E theta direction is minus theta dot ER. You can use those two properties to differentiate and make all these equations. So you might ask yourself, where might we use cylindrical coordinates? And here, in a roller coaster. Where else? So I'm going to show you guys an example of how to use cylindrical coordinates. So we have a plane P flying along at an angle 10 degrees in a straight line. It has velocity 360 kilometers an hour and an acceleration of 0.5 meters per second squared along a straight path. We need to find r dot, theta dot, and z dot after 2 minutes. So firstly, we need to convert v naught into SI units, so meters per second. So we just divide 360 by 3.6, which gives us 100 meters per second. Next, we need to find the velocity at 2 minutes. So we just use this kinematics equation, Vt is equal to v naught plus at, which gives us 160 meters per second. Next, we need to find the displacement s that the airplane travels, and s is going to be equal to v naught t plus half at squared, which is equal to 160, which is 100 times 120, plus 0.5 times 0.5 times 120 squared, which is going to be equal to 10,500 meters. So we have this displacement here equal to 10,500 meters. Next, we want to find this distance along here, which we'll call y dash, which is kind of like the horizontal displacement. So y dash is just going to be equal to 10,500 cos 10 degrees from here, which is equal to 10,340.50 meters per second. We can also find the vertical displacement, z, which is 10,500 sine 10 degrees, which is equal to 1,823.31 meters. We can also find this angle theta now. So we go theta equals tan inverse of 10,340.5 divided by 4,000, which is going to be equal to 68.85 degrees. Also, we can find r, this distance along here from the observer to P, the horizontal distance. So r is going to be equal to just the square of the components, 4,000 squared plus 10,340.50 squared, just from here. That's going to give us 11,087.20 meters. Now we can start finding the velocities. First, we'll set up two vector triangles. We have this one, y dash, which is looking at this face here, z, and that's going to be s. We have vxy, vz, and that's v. So we can say that vz is equal to v sine 10, which is equal to 160 sine 10, which is equal to 27.78, which is equal to z dot. If we look at our original equations, the velocity in the z direction is just z dot k, so we've already found the first part of the question. Next, we find vxy, which is equal to v cos 10, which is 160 cos 10, which is going to be equal to 157.57 meters per second. We'll be using this later on. So now we can set up a second triangle, which is going to be looking directly down onto this face here. So you'll have 4,000 meters here, and then you have y dash here, then r, and you're going to have v xy you're going to have VR, you're going to have V theta. So here we can say that V theta, which is equal to R theta dot, is equal to Vxy cos theta, which is equal to 157.57 cos 68.85. Remember we found theta just up here, which is equal to 56.85 meters per second. From there we can say that theta dot is equal to 56.85 divided by R, which is 11,087.2 from here. This gives us theta dot is equal to 5.13 times 10 to the minus 3 radians per second. We can also work out R dot, because we know VR is equal to R dot. Again, from these equations we have VR equal to R dot and V theta equals to R theta dot, which is where I got this from before. So we have VR equals R dot is equal to Vxy sine theta. So this is going to be equal to 157.57 cos 68.85, which is going to be equal to 146.96. So therefore we have R dot is equal to 146.96. So therefore we have almost have three components. We don't quite have Z dot yet. So there's Z dot, there's theta dot, there's R dot. Next we'll be working out it via the spherical coordinates. So here we are solving with spherical coordinates for R dot, theta dot, and phi dot. I've just set up two vector triangles to begin with, which are just projected from the original one. This is a look from top down, and this is just from this side here looking at phi and z. So it's quite simple to set that up. You guys can figure it out. From here we can work out phi, and all this data is just taken from all this previous example. So if you just refer to that. So we have phi is equal to tan inverse of 1823 on 3.1 divided by 11,087.2, which is just from here, which gives us 9.34 degrees. We can also work out R, which is equal to the square root of 11,087.2 squared plus 1823.31 squared. This just gives us 11,236.12, which is the distance here, R. Next we can work out VR, which is just equal to R dot. So VR is just here. It's just the velocity in the R direction, in the radial direction. So that's going to be equal to the components of VR, V little r, in the V capital R direction, and the component of VZ in the VR directions. That's equal to VR cos phi plus VZ sin phi. And that's going to be equal to 146.96 cos 9.34 plus 27.78 sine 9.34, which is simply equal to 149.52 meters per second. Then we can work out V phi similarly. We have V phi is equal to R phi dot, which is going to be equal to we have positive z, so Vz cos phi, and then we've got VR in the negative direction, so minus VR sin phi, which is just going to be equal to 27.78 cos 9.34 minus 146.96 sine 9.34, which is going to be equal to 3.56 meters per second. Next we can work out phi dot just by dividing by r, so that's going to be 3.56 divided by 11,236.12, which is going to be equal to 3.17 times 10 to the minus 4 radians per second. And we also have theta dot, which is just equal to 5.13 times 10 to the minus 3 as per the previous example. So that's how you find the velocity for cylindrical coordinates and for spherical coordinates. You usually just use vector equations and find the ones in those directions. Thanks for watching. I hope that was a lot of help.